I'm not going to spend a lot of time talking about trace element geochemistry from a paleoceanographic perspective, but what I want to do is use it as a way to lead into the frontiers of geochemistry. And I see, because there are some wonderful tools that are coming on, that are online now, that dovetail beautifully with stable isotope research. And back in the around 2000, my colleague David Lee and discovered, and Yella Baima discovered that if we look at foraminiferous shells and we look at the trace element geochemistry, that magnesium, the magnesium content co-varies with temperature. This became a big thing because it allowed us to go out now and reconstruct sea surface temperatures without the ambiguity of not knowing the delta O18 of the water and oxygen isotopes. And this is just an example of a 500,000 year record from the tropical Pacific. This is sitting out on the Ontong Java Plateau, which is out towards Australia and the Great Barrier Reef. And this is the just north of the Galapagos Islands on the east side. And you can see glacial, interglacials, and you're looking at about a now 2.5 to 3 degree temperature change. It's these data that have allowed us to have a pretty good estimate of the climate sensitivity to a doubling of CO2. Okay, because we were able to look at the tropics, and the tropics really should only be affected by CO2. Insolation changes are negligible in the tropics. Okay, so magnesium calcium really opened up a world that we were able to start going after temperature, and by linking it up with oxygen isotopes in foraminiferous shells, because you're working with the same material. Okay, as a grad student that I had, Matthew Schmitz, now at Old Dominion. Okay, we were able to start reconstructing the hydrologic system in the Caribbean and how ocean salinities have changed with movement of the ITZZ and things like that. Now, magnesium calcium is pervasive. It is one of the dominant tools used in paleoceanography. Okay, the problem was that some researchers started to point out a problem with foraminiferous shells. And that problem was that magnesium wasn't homogeneous throughout a foraminiferous shell. And this led, when I was at the National Science Foundation, I had an opportunity to visit a colleague, Steve Eggins, out in Australia, and for the first time I got a taste of laser ablation ICP-MS. So you're looking at a foraminifera, and those holes are made by a laser, an excimer laser, 193 nanometer laser. Okay, and we can laze through these chamber walls and measure the elemental composition and ratios of this material. The shell walls are only about 30 microns thick. Okay, so these spots are on the order probably about 40 microns, and they're hooked up to a quadrupole, but you can hook this up to a high resolution ICP-MS, or you can hook it up to a multi-collector. You can get amazing data now with very, very high spatial resolution and analytical precision. Okay, and basically what these lasers do, this is just a calcite, spark calcite, is they pulse at the surface of a material, and they literally vaporize it. And they vaporize down 100 nanometers into the surface. The next pulse comes, another 100 nanometers, and so on going through. And every time you get one of these pulses, as I learned not too long ago, that we're talking about temperatures in this plasma that comes off of north of 10,000 Kelvin. So it's really hot. This stuff comes up as a plume, and it's swept off, and it enters into the ICP, the inductively coupled plasma mass spectrometer, where we're able to now measure the elemental composition in that plume of gas. And you're pulsing at 5 hertz or 10 hertz, so you're moving through a material and you're getting a continuous record. So you can take a otolith, we do a lot of otolith work, and you can do a transect along an otolith, and you can get the elemental chemistry using a laser in no time flat. And it's really wonderful. And as you pulse through, you can see 10, 20, 500 pulses. You're moving through the shell and looking at the geochemistry of the shell. Now, when you take a look at Orbulina, which was the organism that we used to calibrate this magnesium thermometer, this is now a cross-section through the shell. There's our sphere. And if you look through the shell, you can see on the inner surface, it's kind of smooth. It's really rugged on the outside. So we pulse from the inside out. And right here, you have this POM this is the primary organic. They used to call it membrane. There is no membrane about it. It's basically a organic layer that's rich in amino acids. We now call it a sheet. Problem is that we use POS. People started laughing all the time. It's the primary organic sheet, but anyway, that's what we call it. So anyway, so if you lace through this, this is what you find. So this now is a nanosims image. SIMS is a secondary ion mass spectrometer. This is an image of magnesium bands in the wall of an Orbulina shell. So here's the inner surface, the outer surface, okay, inner to outer, and you're going through, and this POM area sits right about over here, and you can see this very continuous layering of magnesium in the shell. And when people saw this, they went, there's magnesium dead as far as the thermometer goes. Because when you look at these elevated magnesium values, it would say the ocean temperatures were 45 degrees, and it's impossible. We did a series of experiments now using the laser. All right, we took Orbulina that we grew in the lab, and this now is a laser ablation profile going from the inner surface to the outer surface, and you can see this. You know, the bands here aren't full because the laser is actually averaging out. They're really, really close. They're several hundred nanometers apart. And then once we get past the primary organic membrane, these are separated by 2 microns, so you can get these really nice bands as you move further out. You can even see how the magnesium increases to the outer surface, and you see that as we move in the laser. And we were asking the question, what causes the bands? Why is it happening? And one of the things that we learned early on in our first experiments with Orbulina was that it's a great geochemist. And we found that if you change the barium content of seawater, the shell geochemistry, the shell barium content changes proportional to seawater. And we found that barium going through the shell is constant. We don't see any of this variability. So that's biological and that's inorganic. It's just being incorporated into the lattice proportional to what's in the water. Okay, so what we realized was, hey, let's just take our species, our Orbulina individuals, okay, and because barium in seawater and the foram covaries linearly, okay, all we have to do is move this foraminifera back and forth in a jar of water every 12 hours, okay, and watch to see what happens on a diurnal basis. And we learned that, okay, blue is magnesium, the solid line, the dark line now is the barium that we changed the water on, and we found the spike during the day would correspond to the low magnesium. This is day-night calcification. There's something going on fundamental that's causing the magnesium content of the calcium carbonate to change on a diurnal basis. Okay, and we're still working on why this happens. I lean towards the fact that it's related to mitochondrial uptake of magnesium during calcification. This is a really cool laser confocal microscopic image with using vital stains. In this case, red is a mitochondrial stain, blue is a chlorophyll stain. Okay, so you can see the mitochondria all on the surface of the shell, and these are all the symbionts inside the shell, these symbionts. And they're rich in mitochondria. We think the mitochondria migrate in and out of the foram on a day-night basis. All right, and the reason we think that, as you'll see in a few minutes, is this is what the symbionts do. There's a light cue, and the symbionts move in at night and they move out during the day. They vacularize. I want to come back to that. I don't want to go into that right now, but you'll understand why. I want to do that in a second.
So the mitochondria you're talking about the foraminifera migrate in and out?
Yep.
It's not the symbionts?
Both do. The symbionts do. I believe that the mitochondria also do. We haven't been able to quantify how much the density of mitochondria at night versus the density during the day on the surface of the shell. This is the technique that we'll probably use to go after the density of mitochondria on the surface. Okay, but I believe that they migrate in and out, as do the symbionts. Okay, and I'll show you why in about 10 minutes. Okay, so working with a laser ablation led me to start thinking in terms of other instrumentation and what we could do. One of them was a SIMS. So we have a SIMS, which is a secondary ion mass spectrometer, and we have a nano-SIMS. The big difference is that the SIMS, okay, allows us to have analytical or spatial precision, okay, resolution of 2 to 5 microns with very, very good analytical precision. So we're talking about, for oxygen isotope geochemistry, plus or minus 0.3 per mil. NanoSIMS gives us nanometer scale spatial resolution, okay, but it loses out on the analytical precision. So we're dealing with 5 per mil or 4 per mil, okay, resolution with the nanosims. All right, it's a big difference. So the SIMS, we wanted to go out, just ask the question, okay, can we measure the geochemistry of a band, of a layer of calcite that we insert in the shell in the laboratory? We grow the foraminifera for 1 or 2 days where we change the delta 18 of the water by 20 per mil. Can we pick that up as we scan across the surface of the shell? These are 2 micron spots with the SIMS across the wall of an orbulina shell. Okay, and if you offset them in these transects, you get a really, really nice profile. This is a control specimen that this was, by the way, this is Spider Vetter was a member of SIRFER circa, I don't know, something probably about 2008, 2010, something like that. And she ran this, and you can see we get very nice spot averages, okay, versus predicted. We inserted an elemental band with barium as well as an isotope band. So here's our barium going through the shell, 2 different specimens. And here's our background, our ambient versus our experimental. And you can see we were able to pick up a 20 mil range in the shell using the SIMS. This was a proof of concept. What researchers are doing with this, okay, well, by the way, we also do this with carbon. So you can do carbon isotopes with the SIMS. You need a bigger spot. These are about 8 micron spots. Okay. What researchers are doing now is they're using things like otoliths with 10 micron resolution to look at migration patterns. So these are 2 papers that were produced, one on bluegills and another one on yellowfin sole, looking across the otoliths and looking at the oxygen isotope geochemistry. Okay, these are in microns, so this is 100, 300, 500. All right, you're looking at 8 to 10 points per 100 microns, 150 microns. And you're really able to pick up seasonality, okay, or in this case of the bluegill, if I remember correctly, okay, you're able to pick up what part of the lake area that they were growing based on the temperature, okay. So SIMS is now finding its way into a lot of research where spatial resolution becomes a problem for your typical analytical techniques. Remember, a 2 to 3 micron spot, even a 5 micron spot, you're dealing with picograms of calcium carbonate. Okay, really, really small amounts, and we can do measurements now that have analytical precision approaching gas source mass spectrometry.